Well, hello everyone. Thank you for attending this presentation. My name is Arnaud, and right now I'm a senior software engineer at Collabora. So I'm mostly a software guy, doing low-level development regarding kernel, drivers, bootloaders, and all the base system stuff, and mostly in embedded software fields. Prior to that, I used to be, a couple years ago, the owner and only person actually at Hawaii Amplification, which was my small company. I was designing and building custom tube amplifiers for guitar and bass guitar. This was actually my first real-world experience with electronics design, and that's why I got interested in the first place in the EDA tools and all the free software tools about that. So I will guide you from going from the idea to the prototype using free and open source software, and just fixing some little thing here. Sorry about that. Okay. There, should be better. Sorry. So going from the idea to the prototype, so I'll walk you through a sample workflow, which is actually my workflow for designing new electronics device. And I'll show you along the way a few software I use or intend to use or just heard about, which are all free software, of course. So first is testing and validating your idea, getting sure everything will work and should work. Then you have the PCB design itself. And finally, you can build a case for your project using mechanical CAD tools. So for the first part, the first questions you have to ask yourself when you have a new idea, might be innovative or just a new take on all the classical circuits, is can it work? There you're a bit on your own. It's about theory and electronics understanding and the basic rules. So you have first idea. If it can work in theory, the thing is, will it work with how you intend to implement it? And in that case, you have, of course, the calculation you can do, but you have also the simulation tools, which are really important. And I guess there are two main simulation tools available in free software too. There are QX, which is a cute one, and based on, I don't remember the engine name exactly, but it's not Spice. And you have ngSpice, which uses the classical Spice tool for simulation. I don't really have any experience with any of them, because I'm not really using more simulation. But the thing I can see here is that ngSpice will allow you to use one of the many models of SPICE devices you can find on the internet. In case you need to use some kind of exotic component, in my case it was electron tubes, which are not really widely used among the electronics community right now. You have tube models for SPICE, but you don't have one for QX, I guess. Then you can draft your schematic. So, of course, you can use a full-featured EDA, but you also have the good old paper stuff. Generally, when you start a project, you only draft your schematic on a piece of paper, and it will be awful, but it will be a fast way of putting your idea into something a bit concrete. And there's also a small software that I really like. It's JSkim. It's really aimed more at analog design, and most importantly to me, it includes an electron tubes library. It is a small multi-platform software. It's written in Java, so it can run on Windows, Mac OS, Linux, any BSD you want. And it's, of course, open source software, and it really is appropriate for drafting quickly a schematic without asking yourself too much question about the design rules or the net names or anything like that. Once you have your theoretical idea validated, or at least you think this can work, you have to make a proof of concept. Basically, I like to talk about having a functional proof of concept, that is taking a small piece from your final circuit to check if it will actually work. It might be, for example, reading an analog voltage in a specific way, and this you can do with off-the-shelf modules most of the time. You have modules from Adafruit, SparkFun, Studio, and so on. You can use a breadboard or a prototype shield, just things that are for an ephemeral circuit design. Once you have your proof of concept validated and you're sure at that point that every block from your circuit is going to work as you expect it to, you have to select your components. My advice on that is that you rather use widely available components, not something from an obscure vendor located in, you can find only on 1 or 2 websites, and you don't really know about the future of the availability of these components. They must have available, comprehensive, and correct datasheets. That is paramount. You have to really be able to know how the component will work depending on what are your inputs and the circuit around it. So the datasheets are really something that is fundamental when you select your components. Of course, it has to have sufficient performances. And a small one that is rather really personal, but I really prefer through-hole mounting components. Don't forget that I mostly work with electron tubes, which are big devices, and all the components surrounding the tubes are high voltage capacitors and power resistors. So I'm used to working only with rather big components. Of course, if you're using a microcontroller in a TQFP package, you won't be able to do that. But for someone who has not real experience in soldering, starting with through-hole components is really easier, way easier. So then you have what I call the proto-prototype. It's kind of a general proof of concept. You put all the bits and pieces together, and then you check whether you can make your whole circuit work. It's used to validate the global hardware design and how every piece will interact with each other. You have to make generally lots of trial and error, so pick a modification-friendly platform. I mostly use Vero boards, as they allow me to switch the connections and easily solder and unsolder many components. But again, I'm working with through-hole mounted components. And it's really not a prototype yet. Here you have an example of one of my prototypes. It was a tube curve tracer, actually, with you can see the Arduino for the digital part and all the analog circuits on the right. Of course, it's something quite ugly, it's fragile, and maybe dangerous because I'm using here voltage around 250 volts. But you get the idea. It's something you don't intend to show off, but it helps you really advance in your hardware design and fix most of the problems you will have in the future. In that case, it was using the right operational amplifiers, because I really had to use JFET input amplifiers, and most of the time, due to offset problems, I didn't get the right results, so it really helped me select the right component for my final project. Once you get to the point where your hardware design is validated, you can finally design the PCB itself. So for a long time, you were only able to use proprietary software for real-world projects. You had already open source software, but in my opinion, most of the time you couldn't use it for to build a project from the ground up and get to the manufacturing. I'm talking mid 2000s right now. Right now we had, in my opinion, two big free and open source software suites, which are CAD, of course, or CAD. Sorry, I'm pronouncing it out of French, and Fritzing. I'll start off with Fritzing. It's really a nice piece of software. It's the most recent one. Actually started, the first version was released in 2008, so a bit more than 10 years. It has a maker approach. It's really maker oriented, in my opinion. You have some graphical views and a really eye candy interface for someone who's not used to the EDA software in general, and it gives him lots of advantages. First off, having the fully integrated stack. In fact, you have the schematics design, the PCB routing, and even an Arduino IDE inside the same software. So you can do all your building and coding if you use an Arduino or a Raspberry Pi microcontroller or so inside the same software. So that's, to me, the big advantage for people who want to create a first project, or at least are not really used with the whole development process of a connected or intelligent device. It has a really user-friendly interface. As you can see here, this is really easy to visualize what you're doing and how you're doing it. There are multiple design modes too. Here you can see the breadboard mode and the schematics capture mode. And you can switch from one to the other, and every connection you make on the breadboard mode will be transferred to the schematic mode, and so on. And most of the modules available on the market and the microcontrollers, such as the Arduino, Raspberry Pi, even the Galileo and a few other ones, are available in the default library of the software. So when you're using off-the-shelf modules and development board like these ones, this is really a big time saver. But of course, has a few drawbacks, at least in my opinion. The library is quite limited only to popular and most available components and modules. For instance, it doesn't have any electron tube related components in the default library. So that's really something that I, for myself, cannot use. New model creation is quite difficult because it has as the things are really all nice looking and really nicely integrated, you have to put more effort into creating a new component for Fritzing with having a nicely drawn component footprint and images than you will do with the traditional EDA software. So it's not something that you can't overcome, of course, but it requires a bit more time and a bit more involvement. The auto router for the PCB stuff is quite poor, I have to say. I've only tried it really quick, so maybe I'm wrong, maybe some of you will disagree, but from my experience, the auto router is really quite almost unusable and not on par with what you could expect of a professional EDA package. And finally, it's quite difficult to use for complex or exotic projects. By exotic, I mean some projects using electron tubes, mostly. But I'm sure some other people would have different use cases. And maybe going through with an FPGA on a TQFP 144 package will prove to be a bit more difficult using Fritzing. But then again, if you getting to using this kind of packages, maybe you're not the target audience of Fritzing. So you might rather use CAD. This is the Elder. It started in 1992, so a really old piece of software, even by today's standards. And it's the most widely used right now in the industry regarding open source EDAs. I've seen Olimex is an obvious big user of CAD. And Purism, which is designing currently a smartphone running Linux, has designed their dev kits, the dev boards for the smartphone using CAD, and they intend to make it public and open source. So I hope they will deliver up to it. But that's also a big industry user of CAD. CAD is not as integrated as Fritzing. You have two big software which are quite independent. You have eSchema and PCB-New. The first one, of course, is for schematics capture, and PCB-New is the PCB router. It includes also a lot of useful tools, such as a PCB calculator with a lot of functionalities. For instance, this allows you to calculate the heat elevation of a track depending on its width and the current and its length and the current drawn and passing through this track, and other really useful stuff that are a great help in the design stage. And it has, to me, some big advantages over every other open source EDA package. First, it is very actively developed, and I have to say the CERN, which is the European Center for Nuclear Research, is devoting a few people working full-time on KiCad. And first starting using this software, or at least I tried to use it, before their contributions. I believe it was version 3. And starting with version 4 and the CERN contributions, we really had a software which make a great leap forward in terms of usability and features, and they really did an amazing job on that, and it keeps getting better. So that's something that's wonderful. The library by default is quite comprehensive, and it even includes valve, electron tube symbols and footprints. You have also lots of third-party libraries. As it is quite an old software, you have lots of people who have used it over the years, and you can find virtually any component. If not in the default library, you will be able mostly to find it in a third-party library. It has advanced routing abilities, like the push and shove router, the routing of differential pairs with having the same length for every track. And it integrates a simulation engine based on SPICE and 3D preview. Of course, everything is not perfect. Mostly, the interface is not really user-friendly for a first-time user. You have to understand the way KiCad works and how every software integrates with the other. And regarding the use of the mouse wheel and keyboard shortcuts, it's not really something intuitive at first sight. The user interface, so I know that's something that's been worked on right now, but between the schematic editor and the PCB designer, you have really some inconsistencies in terms of user interface and user interaction. So that can be difficult at first when using KiCad. And that's, I guess, being worked to also, but the two software don't communicate enough. You don't have, for now, when you change a connection in the schematic editor, it's not automatically pulled back in the PCB design. You have to go through the netlist export and import from the PCB-New in order to make it to have the change available in the PCB editor. So my advice is that you better use Fritzing if you had no prior experience with EDA software and electronics design, And then when you get comfortable enough with it and need more features and more advanced capabilities, go on through KiCad. Then you have to manufacture your PCB. You can do it at home, but it needs specific equipment and you need also some space. It requires using some toxic products, so it might be dangerous. And it's also quite difficult, at least when you start, for double-sided boards or when you get thin tracks and really little spacing between tracks. It's quite difficult to have a clean result. So my advice is rather to go through professional manufacturing. You have lots of it now. It's really cheap for small PCBs. You can have 5 by 10 centimeters PCBs. It would cost something like 20 euros for 10 pieces, including the shipping costs. The drawback is that you have to order generally 5 to 10 PCBs minimum. And there are lots of manufacturers to choose from. You have a website which is PCB Shopper, which is really nice and compares the prices and delays of every manufacturer, or I think there are every manufacturer, given the size and a few technical requirements for your PCBs. Other useful software, which are Horizon, which has been presented just before. Actually, I didn't know it before I looked at the schedule for this room at FOSDEM, so I really give it a try. And it's more modern EDA. It uses KiCad's router, so I guess you can definitely do something with it. You also have GEDA, which is an old project, but seems to be lagging behind KiCad for quite some time. And something that I found a bit fun, it's Visolate. It's an old project, no longer maintained, but it allows you to generate G-code for building a PCB from a milling machine. So that's another take on PCB manufacturing, which you can do in your local fab lab. And I think it was interesting to mention. Then I get real quick through the next slides because I'm really light, sorry. So for designing a case, you have some mechanical CAD software available. The first one being LibreCAD. It's some kind of digital drawing board, 2D only, like you may have heard of AutoCAD in the 90s. It's really the free software equivalent right now. Quite useful actually for doing laser cut, like this case, for example. It will be drawn nicely on LibreCAD, but of course you can't do anything which will be 3D printed with it. Then you have OpenSCAD. This is mostly, I think, of it as the software developers mechanical CAD, where you code your shape and have only a 3D preview, but you can't interact with. And finally, there is FreeCAD, which is a more traditional approach and has a parametric 3D modeling. The user interface is more close to the industry standards, and it has a classical workflow, which is you design a sketch in 2D and then through extrusion or rotation get a shape from it. And that's all for me. I don't know, maybe we have time for one question, but I guess we're running really late, so sorry about that.
Have you tried the freely distributed version of commercial software like Eagle or old PCAD?
The question was, did I try the freely distributed commercial software? So proprietary software, but not paying for it, such as Eagle. I've tried it back in 2005, I guess. But since then, I'm a long-time free software advocate. So when I found I was looking for a new EDA software 5 or 6 years ago, I obviously wanted only free software.
Actually, my friends switched to CAD from Eagle. While they have small commercial company, they can pay for it, but they still switch to CAD because they become better. They don't.
All right.
Any other questions? Okay, let's thank Arnaud again.
Thank you.